Welcome everyone to the channel. So, part 2 of our adventure. Here is this little box. I'll try to take it apart. First, I think I'll cut it here on the grinder. Grind down this plastic on top. And then I'll heat up this compound with a heat gun. And pick it off bit by bit. Right, well then now I'll go to the grinder to sand off what I can. And I'll be back. So, I've ground down these bevels to see where the compound starts and where this epoxy ends. Now I'll try to remove this plastic, the part that's left here. But this compound has very high adhesion to plastic. It doesn't just flake off easily. Now I'm going to heat it and clean it off. When heated, the plastic and compound soften, and therefore can be removed very effectively. Look at this. Well, that's just the plastic heating up. But the compound softens as well. See how it slices off in these layers. So I think this way, I'll manage to clean this board. Right. So, I probably need to slightly lower the temperature, because a diode or a Zener diode has already desoldered. Yes, here it is. I'll put it aside so I don't lose it. Okay, everything's fine. I've cleaned this board. Now I'll solder back the component that I accidentally tore off. Actually, I didn't tear it off. It desoldered from the heat. Alright, great. It's back in its place. So, everything worked out for the best. I've picked off all this resin and identified the component names. This is a 3525 PWM controller. This is a logic chip, and this is a multivibrator. It's an LM393. So, there is no microcontroller here. Everything can be easily replaced, and there's a very high probability of repairing it. I think it's logical to check the operation of this PWM controller. So, I've installed this board. This way, I'll solder wires to it, and it will be possible to check its operation. Alright, so let's continue figuring out this board. I've soldered it here with wires so it's convenient to measure the voltages. Just a reminder, this board isn't working. It receives all control signals and voltages, but it doesn't output the pulse generation for these inverter transistors to charge the capacitors. So, let's quickly check which commands and voltages are reaching it. So, pin 12 is R0 GND, pin 11 is plus 12V. Let's measure. It's there. 12V. Supply voltage is present. Now, the command that enables generation is the fourth pin. Just a moment while I connect. Okay, switching on the capacitor charge start. The signal has arrived. Now let's check if there's generation or not. These are the 10th and 9th pins. 10th, nothing there. On the 9th, same thing. Basically, it's all clear. There's a PWM controller chip here, the SG3525. Here it is. Now let's check its operation. In most cases, the operation of this chip is controlled by two pins. These are pin 10, shutdown, and pin 8, soft start. If voltage is present on pin 10, then this chip will be in an off state, meaning it won't work. Currently, there is no voltage. Now, let's check the supply voltage. Supply voltage is on pin 15. The supply voltage is there. Good. So, it's 0V here. That means it should be working. There's no lockout. Alright, let's check the 8th pin. Soft start. It's located right here. There should be voltage on it for this chip to work. If it's 0, then it isn't working. Now we see 0V, even though there should be voltage. Only a capacitor is connected to it, which is connected to ground, the common wire. So something is wrong here. We'll figure out what the issue is. The capacitor is right here, and accordingly, there's no generation. I'm measuring it. Let's check pin 5. There should be generation with a sawtooth waveform. Generation is present. Good. Oh, voltage appeared on pin 8. Let's see, generation at the output of this board. Yes, there are pulses. This board has started working. What happened? I moved this capacitor a little bit. Or maybe something else? Maybe this chip warmed up. I don't know. Well, it's not even a great sign. If it's working now, because I don't know the reason why it wasn't working. Now I'll turn it off, let it cool down, and check it again. So, I've started the machine again. Checking the voltage on pin 8 immediately. It's there. Generation is present. So, this board is now working correctly. Generation is present. Everything is fine, but what it was is still unknown. Well, in this situation, I should probably replace this PWM controller. It's under suspicion because there was no voltage on the 8th pin then, but now there is. And this capacitor, maybe it was shorting that 8th pin to ground, and now it's somehow recovered. I don't see any other options, so now I'll replace this chip and the capacitor. Then I'll be able to test the machine. So, I've replaced the chip and the capacitor. I couldn't find an SMD capacitor, so I used this leaded one. Here is the old chip. I just clipped it out of there. It's safer for the mounting, because it was still on compound underneath, and trying to dig it out of there is quite problematic, so it was better to just cut it off and then it was easy to remove the remaining compound. And here is the capacitor. If you can see it, that was in there. Instead, I put in the leaded one, but it's holding well. Now let's check the operation. Let's immediately connect the oscilloscope to the generation output. Switching it on. Generation is present. Generation is present. Yes, there's pulse generation. If you can see there, roughly speaking, 45 kHz. Alright. Everything's working as it should. It's good that this defect showed up during the filming, because if it had appeared at any other time, I would have started doubting if there really was zero here. But now I'm sure it was zero. Now there's voltage, then there wasn't. And after some manipulations in this area, the chip started working. And there can only be, I'll say it again, only two reasons. Either this capacitor was shorting to ground and zeroed out that voltage, the 5V that's there now, it pulled it to ground. Or it was a faulty chip. I can't imagine any other reasons here, because in terms of the layout, this 8th pin doesn't go anywhere else except to minus/ground through the capacitor. So both the chip was replaced with a new one, and I soldered another capacitor here too. Rule out a recurrence of such a defect. Now I'll fully check the operation of the device, how it charges the capacitors, and then after that I can solder this board back in place. Let's continue. Here's the board soldered on wires as it was. I've connected the oscilloscope to the output to the capacitors so it will show the voltage on the capacitors. One mark on the screen is 200V. 200V per division. Alright, switching it on. Let's see if this unit is charging the capacitors or not. Okay, the lamp turned on. Now I'm switching on the capacitor charge. I'll turn it on for a very short period, and then, if all is well, I'll turn it on for longer. I've turned it off. We see that there's voltage on the capacitors. It's now even near 500 V. Good, now they're discharging in the off state. Now I'll try to turn it on for a slightly longer period. Alright, the voltage on the capacitors has capped at the level of, what is that, 600 something volts. And it's maintained at this level, recharging slightly. On the oscilloscope, we see that the capacitor has charged to a bit over 600 volts. These steps are when the capacitor has charged to the set voltage, the voltage limiting system triggered on the capacitor, it discharges. And when the voltage drops to a certain level, it recharges to the set voltage again. Good. Everything's working normally. We can even check now if there are flashes of laser radiation. So, here's the laser emitter itself. Inside, there's a quantum radiation generator installed, meaning the laser. Now I'm doing a flash. If you can see, here is the site where the flash will hit. Done. And you can see the pulse on the oscilloscope. Good. Well, that's minimum energy. Let's test at different levels. I've set the oscilloscope to a sensitivity of 500 V per division. Now I'll raise the voltage to increase the pulse energy. So, 1000 MJ. Firing the flash. You can see even a bit of smoke came out. Done. Now I'm switching to 2000 MJ energy. Firing the flashes. Done. It works. Now I'll set it to the maximum 4700 MJ charge. Over 1000 V on the capacitors. Firing the flash. The flashes are quite powerful. Good, the test is complete. I can probably put this all back together, put this board back in its place, and assemble the device. Right. Well, I've soldered the module back in here. Now I need to assemble the pulse-forming unit. Everything's in place. Here's the module. Alright, this unit is assembled. It can be put back in place. So, I've assembled this machine. It's now fully put together. All panels are in place. All units are inserted. Now we can proceed to the Final checks. I'll select the settings here. Manual mode. Let's start the check with the minimum energy value. Here's the handpiece itself. Opening the aperture. Turning on the lamp. Turning on the operating mode. We'll test. On this target. I'll do it in order. In this box, I'll fire a flash at minimum energy. Here at medium, and here at maximum energy value. First from a close distance. So, minimum value. Now the medium value. Now the maximum energy value. You can see that the minimum value is significantly different from the maximum. Now I'll do the same but from a long distance. The handpiece is out of the shot now, but the distance to the target is 50 centimeters. Firing into this square. You can compare it with these values. This was just practice, you don't have to count it, but this is what we did at close range, and this is at long range. Now, I'll fire a flash at medium energy and maximum. This is the medium energy value. Now firing at the maximum energy value. So, here too you can clearly see that the minimum energy is significantly different from the maximum. We can estimate the diameter of these marks and these. This is from a short distance, this is from a long one. The diameter differs, but not that significantly. We can conclude that the laser beam for this specific application is quite parallel. Right. And then we'll do the final check, how the device generates a series of pulses. Now I'll fire a series of pulses on this strip. Great result. So, this device can be considered repaired.